Hello and welcome to this pvlib Python tutorial. In this video, we will learn how to define a PV system with two differently oriented arrays. That means that one string of modules is going to be oriented to the east and the other string of modules is going to have an orientation to the west. For this, I'm going to start with the basic definitions of location and system, which we used for the single and dual axis tracking examples. I'm going to copy it all the way down to the line where we define the clear sky weather data. I'm going to copy this over and just delete the definition of the system itself and the model chain here. Also, we're not going to be using the abstract or single axis tracker mount, but instead we're going to use the fixed mount because we don't have any more tracking in this example. Both strings are just going to be fixed. So we have one string. We're going to have one string for each array and for modules. So how do we now define this? We're gonna use the array we've already used in the previous example, but this time we're gonna create two of those. So we're gonna create an array of arrays, which we call arrays, and we start with the array, which needs the mount. And then basically the other informations we also provided for the other system specifications. And for the mount, we use the fixed mount, where we pass surface tilt and surface azimuth. The others are optional. So surface tilt. So the angle of our module is going to be 30 as in the previous examples, and then the orientation, which defines the azimuth, which defines the orientation, that way around. So here we're going to start with the west facing array, which is 270 according to pvlib definitions. And we're also going to name this one west facing without the G, west facing array. It's gonna have the module parameters, which we import up here. So module. We're gonna have the temperature model parameters, which we also import above. Temperature parameters, that's it. We're gonna need the modules per string, which we defined in line 13. Modules per string. And the strings, it's not strings per inverter here, it's just strings, but we're gonna take the strings per inverter we defined above. That's our first array. We set the comma and define the second array, which also has a mount. I'm actually just going to copy this part here because most of it stays the same. We're just going to change the azimuth from our west to our eastern orientation, which then is 90. So 180 degrees difference. This is the east facing array, and the rest stays the same. So we have two identical arrays, one to the east, one to the west. Good. Now, the rest is basically what we did before already for the other examples. We define our system. System equals PV system, and we pass for arrays the arrays we defined above, then the inverter parameters, inverter. And from there we define the model chain, where we pass the system and the location. Then we run the model chain. You should by now almost do this by heart. I still have to read. Run model with the clear sky data we get here from the get clear sky location. Clear. Oh, okay. Run this. Okay, no typos so far. So let's look at the results. We can, I'm just going to do this here. As you know, model chain.results inherits our results. And if we now look at the DC results, we get two sets of results. One is for the first one is for the west facing, the second one for the east facing array. And we can, of course, access those just by indexing 0 or 1. So that's what we're going to use to plot it in a rather simple way. You can, of course, do this in a more Pythonic way, but I think this makes it better understandable, hopefully. So we define sub plots. Of course, PLT. This is if you haven't imported matplotlib, please do so. And then we're gonna access these results. Model chain.results.dc 0 for the first one. Dot. What we actually want is the power. So you can look at short circuit current, current of maximum power point, voltage of maximum power point, but what we want is the actual power of the maximum power point. So we're gonna access this column, and then we plot it. Now, in order to kind of like identify which array is which in the plot, we're gonna use the label, and in the same way we're basically gonna access the name of the corresponding array by checking out the system arrays, and there from array 0 we want the name. So basically, we have our name defined here. We then pass this array to the system. And so by accessing system arrays, the first one .name, we get the name. Easy. And we want all our figures on the same axis plot. So we set AX equals AX. I'm just gonna copy this line and change this to 1. Which gives me the result data and the name for the second array. Then I want, well, yeah, let's add a Y label. Do as you please. Output in watts. PLT the label, and of course we want the legend, otherwise our labeling would be unnecessary. Label legend, stumbled over my own words, and PLT.show to look at our graph. Run this. All right. Now, as you can see, for our location, the sun rises in the east. So we first get an energy yield from our eastern facing array, and then towards like 1 o'clock we reach the south, and then it shifts to the west, and our western facing module takes over. So this is the DC output, as you can see here. So now let's add our total energy yield, the AC, which we defined then here in the system with our inverter. So we say model chain dot results dot AC dot plot, and we label this as our inverter, and we add it to the same axis plot. Axis plot. Yeah, run. And now the green line, you can see it's kind of like putting both energy yields from the east and the west facing array through the inverter gives us our AC energy yield. Actually, this example was somewhat inspired by an example from the official pvlib website. I'm gonna put the link to that example in the description below this video. They have a slightly different approach here, but they also show a more Pythonic way of plotting this. So if you're interested, head over there and check out that example, and of course check out the other examples as well. They go beyond what I showed so far here. But that's it for this video. Thanks for watching. Thanks for all the nice comments and discussions I get from making these videos. It really is a lot of fun. I hope you liked this video. If so, please give me a thumbs up and subscribe to the channel so other people can find these videos as well and learn about PV modeling. Otherwise, stay curious and we'll meet again for another video. Bye!